Alright, in this video I'd like to talk about the comparison test as a test for determining whether or not an infinite series converges or diverges. So at this point we're really looking at trying to show, so these are proofs really, we're trying to prove that a particular series, like either of these, would converge or diverge for either of these, right? We're not necessarily looking for what they converge to. We just want to prove that they converge or show that they diverge. So let's look at the comparison test here. This says if the terms of the series have these properties. In other words, they're always non-negative terms. If we have negative terms, if mixed in with positive terms, that's called an alternating series. And that's a separate class of series that we need to look at. But for now, we're looking at only non-negative terms. And notice that the terms of a sub n are smaller than, less than or equal to, the terms of b sub n for all n. So let's just, I've written the first part of this. I think we can fill in the rest here if we think about the logic of this. So again, a sub n is smaller than b sub n. So if the infinite series of the terms of b sub n converges, looking at this inequality, then what could we say about a sub n? So hopefully a moment's thought would help you to see that if all of these terms add up to something finite, and these terms, the a sub n's, are smaller than the b sub n's, then this should converge also. Now we turn it around. What happens if we add up all of these terms and it diverges? It doesn't converge to a finite limit, but it goes to infinity. Then what do we think will happen to terms that are all greater than or equal to these terms? Again, logically it makes sense. These would also diverge. The real trick here, if you want to know, generally this will be the series that you want to know something about. We're trying to, like, this is an if-then. We're trying to show that this converges or diverges. The trick usually is finding your comparison, the thing that you know converges or diverges. So let's just look at a couple of examples. So we look at this series here, and we see it looks like, if we squint, maybe get rid of this 2, it looks like a geometric series, right? So let's compare 1 over 2 plus 3 to the n with 1 over 3 to the n. All right, green's getting a little weak. Let's go back to black. So which one is bigger? Which one's smaller? I generally like to look at the denominator. If the denominator is bigger, then that means that its reciprocal is smaller. So clearly 2 plus 3 to the n is bigger than 3 to the n. Therefore, the reciprocal must be smaller. And we know, we can rewrite this as 1 over 3 to the n. And we know that this series from n equals 1 to infinity, that's a geometric series where r is less than 1. So we know this converges. We know each of these terms of the series in question are smaller than each of those terms. So this implies that our original series also, what was it, 1 over 2 plus 3 to the n, that also converges. Okay, let's take a look at this example. Here we have 1 over 2 plus square root of n. So notice some similarity. Again, there's a little bit of squinting involved here, right? If we squint here, we see 1 over 3 to the n. If we squint here, we see 1 over square root of n. All right? So here's the problem. We have the same inequality, right? We have 1 over 2 plus square root of n should be less than 1 over square root of n for the same reasons that we described over here. The problem is, does this converge or diverge? Well, that's a p-series, right? That's a p-series that we could rewrite 1 over n to the 1/2, right? And we said that the infinite series from n equals 1 to infinity for a p-series where p is less than or equal to 1 diverges. All right? So what we have here is that these terms are smaller than these terms, and when we add up all the infinite terms of this, it diverges. So hopefully it makes sense that that doesn't tell us anything about this one. Because it's smaller, it could converge. But it could still diverge too, right? You could be, bigger than infinity is still infinity, I guess is the way to think of it. The point is being smaller, being less than a divergent series doesn't tell us anything about the series in question. So again, it comes back to finding a good comparison series. So I'll just tell you this is true when n is greater than or equal to 4. All right. So again, let's compare the denominators. What we're claiming here, if this is less than this, is that n is greater than or equal to 2 plus square root of n anytime n is greater than or equal to 4. So immediately, and the other thing you can verify is that for n equal 1, 2, and 3, it's actually not smaller. But eventually it's smaller forever. So those first 3 terms aren't going to make a difference, as long as we find a point after which this is always true. I guess before we go any further, why would we compare with this? Well, we know that's the harmonic series, n equals 1 to infinity. We know that series is also a p-series with p equal to 1. And so that diverges. So if this diverges, and all the terms of this, once we get past 4, are bigger than this one, then this series should also diverge. So that's the logic. What we need to do is establish this inequality. All right. So again, for 1 over n to be less than 1 over 2 plus square root of n, what we want to show is that n is greater than or equal to 2 plus n square root of n when n is greater than 4. So I'm going to just rearrange things here and rewrite this as n minus the square root of n minus 2 is greater than or equal to 0. Again, anytime n is greater than or equal to 4. Now, this, you can kind of think of this as like n squared minus n minus 2, where n is square root of n squared, right? You can kind of maybe think of it this way, right? And then this is square root of n. So I can factor that. So that factors into square root of n. Let's see, square root of n, and I got a square root of n. I need numbers that, when multiplied, give me negative 2, and added, give me negative 1. So I want a minus 2 and a plus 1, greater than or equal to 0. Well, again, we're looking at when n is greater than or equal to 4. Is this inequality always true? So when n equals 4, that's 0, and that's positive. For anything greater than 4, that's positive, and that's positive, so this will be true. So we've shown that. Therefore, since the terms of this series are larger than the terms of this series, and this one diverges, then we know that this one diverges. Okay, so you can see, like here in this particular case, things were very straightforward. Here we had a little bit more work to do to establish, to find our comparison series that would allow us to show that the series in question diverges. I will say, however, right off the bat, though, with the kind of the squinting we did of getting rid of this 2, we did show that it should behave like 1 over square root of n, which we know diverges. So at least gives us some intuition about what the series should do. Finding a comparison series is still going to take some work, but at least we can, from the beginning, get at least a sense for whether or not the series should converge or diverge. Okay, so that's the comparison test, but sometimes direct comparison doesn't work. This was a case where we had quite a bit of work to do. There's other cases where it's harder than this to try to find a comparison series, or it's not possible to find a comparison series, at least not for direct comparison. So we have another one called the limit comparison test. So here, again, we're just saying that the terms of the series are all positive. And what we're going to do is take the ratio. We're going to take the limit of the ratio of each term. And if that limit converges to a finite and positive number, all right, so it can't go to infinity, and it can't go to a negative number, then these series converge or diverge together. So this is where our work with sequences will be helpful. So we've got, this is what we said that 1 over 2 plus square root of n should behave like in the example that we looked at previously. And this is where the limit comparison test is actually really pretty useful, because remember, we couldn't use this for a direct comparison since these terms were less than these terms. And so if this diverges and this is less than something that diverges, then this could either diverge or converge. But if we look at the terms, they look very similar. So if we take the limit of their ratio, so 1 over 2 plus square root of n over 1 over square root of n, so we can rewrite that as the limit as n goes to infinity. So we're just going to multiply by the reciprocal. We're going to get square root of n over 2 plus the square root of n. And we know that in this case, there's a lot of ways to do this, but we can just take the ratios of the coefficients of the highest degree terms. So, in other words, this is n to the 1/2 over n to the 1/2 plus 2. We see here that it's going to converge to 1. And since 1 is both finite and positive, then this series will behave the same as n equals 1 to infinity, 1 over square root of n, where that's the same as 1 over n to the 1/2, which we know diverges by p series. It's p series, and with p being less than 1. We know that that diverges. So you can see that this is much simpler than the work that we had to do for the comparison test. Let's look at just a few more examples. So just to separate these out, maybe I'll do the next one in a different color. So let's say we have the series n equals 1 to infinity of 1 over 3n squared minus 4n plus 5. So again, I think what we want to look for is kind of, what are we going to use for comparison? So we can see that probably the easiest way to do this is to think about the highest term, the highest degree term in our polynomial here, and don't worry about the coefficient. So let's just compare it with 1 over n squared, and we know that this converges. Also, it's a p series with p equal to 2, which is greater than 1. So we know it converges. So again, we take the limit of the ratio of terms, and as long as that gives us a limit that is finite and positive, so I've got 1 over 3n squared minus 4n plus 5 over 1 over n squared, so that's going to be n squared over 3n squared minus 4n plus 5. Again, this is going to converge to the ratio of the leading coefficients. That's going to converge to 1/3, which implies that this infinite series, 1 over 3n squared minus 4n plus 5, also converges. Alright, let's just take a look at one more example. So let's take a look at from the series n equals 1 to infinity of the square root of n over n squared plus 1. So in this case, we might have a little bit of simplifying to do. Again, I think this idea of squinting is a useful strategy. Like if we just get rid of that 1, we've got square root of n over n squared, which I could also think of as n to the 1/2 over n squared, which would give me 1 over n to the 3/2. So again, what we're doing is we're just kind of looking at what would the power be if I just took these leading terms and found their ratio. So let's compare this with 1 over n to the 3/2. So I'm looking at the limit as n goes to infinity of square root of n over n squared plus 1 over n to the 3/2. This is going to give me n to the 1/2, just rewriting the square root, n squared plus 1 times the reciprocal, so that's n to the 3/2, so that gives me, well, over 1. So I get n squared over n squared plus 1. Again, that limit I get is going to be the ratio of the leading term, so that's 1. So what do we know about 1 over n to the 3/2? That is p series with p equal to 3/2. That's greater than 1, so it converges. And so by the limit comparison test, then this series also converges. So we looked at two different tests here. One was the comparison test, where we look for a series that converges that would be bigger than our series in question. This is direct comparison. So if this one converges, then the one that's smaller than it converges. Or likewise, if this one diverges, then something that's bigger than it would diverge. We saw with this example that it's not always easy to apply that. It's not always easy to find a comparison series. So the limit comparison can be useful because many times something that p-series is a favorite one. I think if you find something geometric, those are very useful for applying in the case of the limit comparison test. So those are two more tests that we can use to determine if a given series converges or diverges.